So in this video, we're going to work out this line integral. We'll be looking at this scalar function. So we're integrating respect to arc length along the curve of the intersection between this surface and that one. All right, so first we need to find the curve C, and then we'll evaluate. So we know that the line integral along curve C of f ds, this is going to be the integral from a to b of f of r of t, which is our curve C, then times the magnitude of r prime of t dt. And we know these limit of integration, these are the values of t. So we'll have to figure out what is our curve C first in vector form, and then we're going to compute its derivative, and then we're going to compute the magnitude of the derivative. Then we plug everything in terms of t in the integrand. All right, so let's go ahead and do that. So first I'm gonna try to find curve C. So we look at these two equations and we try to find curve C. That's the intersection of the two. So we're given that Z is equal to this right here. So I can simply take that and plug it in here for Z and express the equation in terms of X and Y. So we will have Z, which is equal to 2y plus 1, set it equal to x squared over 5 plus y squared. And then we recognize it's probably a circle or an ellipse, so let's go ahead and solve for it. So we might have to complete this square. So it looks like I'm going to move this term to the right-hand side. So I have 1 is equal to x squared over 5 plus y squared minus 2y. And now we're going to go ahead and complete the square for these two terms because we want to put it in a specific standard form of an ellipse. It looks like it's going to be an ellipse. So we're going to take half of our b value right here, then we square it, so that is 1. So we add 1 to this side, and we add 1 to this side, completing the square. So then on the left side, we have 2, and on the right side, we have x squared over 5. That stays as it is, but the y term will factor into a perfect square, y minus 1 all squared. And finally, we're going to make this a 1, so we divide both sides by 2. So we have 1 is equal to x squared over 10 plus y minus 1 squared over 2. So the curve of the intersection of the surface is actually an ellipse. Okay, so I'll show you a picture later. So let's parameterize this curve. So we know an ellipse is parameterized in the following form. You'll have x is equal to r cosine t plus h. So we know the distance along the x-axis is going to be square root of 10 because you want to write this as some a squared. So I'm going to simply put that as square root of 10. And then y is going to be parameterized as, again, you can think of r sine t plus k. That's the coordinate of the center. So we know the radial distance along the y is square root of 2, because that's how you write 2 as something squared. So we know this will be replaced with a square root of 2, and the shift is plus 1. So plus 1. Now z, what will be the parameterization for z? For z, we know it's right here. So we can use this equation because that's expressed for z. 2y plus 1. So y is equal to this. So we're going to do 2y. That's 2 square root of 2 sine of t plus 1. Plus, sorry, forgot what I said. Plus 1. Okay. And then this simplifies to simply 2 square root of 2 sine of t plus 3. So that is our parameterization for z. So let's just put that right here. And our bound on t will be from 0 to 2 pi, the entire curve. All right, so that is our parameterization for the curve of the intersection. This is for the curve C. Okay, so now we can plug this into our vector form for C. So we'll have x, that's square root of 10 cosine t, y is square root of 2 sine t plus 1, and then we have z, which is 2 square root of 2 sine t plus 3. All right, so that is the curve C in vector form. Now we compute its derivative, so I'm just gonna get myself some room here. So the next thing we're gonna do is find the derivative or r of t. So in, again, vector form. So the derivative of the first component, that's going to be negative square root of 10 sine of t. The derivative of the second component is square root of 2 cosine of t. Derivative 1 is 0. And the last component, the derivative of the z component is 2 square root of 2 cosine of t. All right. And now we find its magnitude. So that is going to be the square root of sum of each component square. And okay, so now we have 10 sine square of t. Then the next component square, that's going to be plus 2 cosine square of t. And the last component square, so 2 square is 4, square root of 2 square is 2, so that's 8 cosine square of t. All right, so all of that is under the square root and combine like terms. So, you know, this will give you 10 of cosine square of t, so plus 10 sine square of t. Using the Pythagorean's identity, we have 10 sine square of t plus cosine square of t. All right, and we know this is our famous identity 1, which means our magnitude of our parameter is simply square root of 10. All right, so we got that. Now we're ready to set up our line integral. So we're looking at this line integral. So I'm just going to copy it down. Okay, all right. So let's now let's evaluate this. So this is our f of x comma y comma z. So we want to replace this as f of r of t, and ds will be the magnitude of r prime of t dt. So we need to substitute all x, y, z in terms of the parameterization, and we also replace ds with r prime of magnitude r prime of t dt. Okay, so this will be the integral from 0 to 2 pi of x squared. Well, x is this, so we're going to square that. That is going to be 10 cosine square of t plus y. Y is this right here. So we're evaluating f at r of t. That will be square root of 2 sine of t plus 1. And then plus z. Z is 2 square root of 2 sine of t plus 3. ds, that is going to be square root of 10 dt. All right, so that is our setup for the integral. Now we continue to evaluate this. Now, you might be able to use some shortcuts, so feel free to use them or just evaluate directly. Now, I'm going to go ahead and combine like terms. So, for example, these two can be combined. So we have the integral from 0 to 2 pi of, let's rewrite. So this is 10 cosine square of t. So that those highlighted terms will give me 3 square root of 2 sine of t and then plus 4 dt. All right, so now we're going to separate this into, so it seems like I have forgotten my square root of 10. Sorry about that. All right, there we go, just rewriting. Now here is something you want to notice. So you have 3 integrals. You have the integral from 0 to 2 pi of 10 cosine square of t times square root of 10 dt plus the integral from 0 to 2 pi of 3 square root of 2 sine of t times the square root of 10 dt. And then the last integral from 0 to 2 pi of 4 square root of 10 dt. So I'm just separating them, and I'm going to show you some shortcut that you can use here. So this is what we have. Now let's focus on this particular integral right here. So focus on the sine of t. So we know that the sine graph, any amplitude, it starts from here, and then it completes 1 revolution from 0 to 2 pi. So this is from 0 to 2 pi. So if you integrate over this period, you have positive area here, negative here. So the net area is 0. So they cancel each other out. And this is also true for cosine t. So we know this integral is 0. So you can save some time. So all we have to do is integrate this and that. So that is the shortcut we're going to apply. But if you want to just proceed with the integration, you may. So we're integrating from 0 to 2 pi of 10 square root of 10 cosine square of t dt plus the integral of the last one, that's from 0 to 2 pi of 4 square root of 10 dt. All right, now here we use the identity. This can be replaced with the identity 1/2, 1 minus is 1 plus cosine of 2t dt, and then we evaluate that. So we have the integral. Now, if you want to pull out the constant 10, square root of 10, we have the integral from 0 to 2 pi of 1/2, 1 plus cosine 2t dt. Now, the last one, this integral right here, well, that will simply be using the power rule of integration. There's not 2, that is 4 square root of 10 times 2 pi. So that's the value of that integral. All right, so let's finish up the very first one. So we have 10, a square root of 10 divided by 2. The integral of 1 respect to t, that's t. The integral of cosine 2t, that will be sine 2t divided by 2. And you evaluate this from 0 to 2 pi. Plus this will be 8 pi square root of 10. Okay, so now we finish up the calculation. So we have 5 square root of 10. Plug in upper limit of integration, 2 pi. Sine of 4 pi is going to be 0. So the lower limit and the upper limit will give you 0 for this portion. So we simply have this plus 8 pi square root of 10, which will simply give us 10 square root of 10, 10 pi square root of 10 plus 8 pi square root of 10. And if you combine them, since they are like terms, we have 18 pi square root of 10. All right, so that's the value of this integral. All right, so now let me show you some graphics of this in a graphing calculator. That way, at least you have an idea of the surface and the curve of the intersection. So first thing we're gonna type in is our surfaces. So one of the surface you had was z equals x squared divided by 5 plus y squared. So that was our paraboloid right here. Then the next surface we had was the plane. So we had z equals to 2y plus 1. So that was the one. All right, so that's the plane. So we can see the curve of the intersection is an ellipse. Okay, so now let's put the curve of the intersection. So we write curve, parentheses. So we put the x component first. That was the value square root of 10. Sine, it was cosine, not like that. Square root of 10. Cosine of t, so that was the x component, comma, then for the y component, we had square root of 2, then we had sine, was our function, sine of t, right here, plus 1, so we have plus 1, and for z we had was 2 square root of 2, so it was 2 square root of 2, sine of t plus 3. So that is our curve C. Hold on, I need to put t and then comma outside. So sine of t and then plus, plus 3. And then our bound on t was from 0 to 2 pi. So we have t, comma, 0, comma, 2 pi. All right, so there you go. That is the curve of the intersection as we anticipated. All right, and if you want to look at the view from the top, it looks like this. So here's the curve of the intersection. All right, I hope this helped you understand this problem a little better. I'll see you next time. Hope you enjoyed. Take care, everyone.